Hello everyone. Uh, it's been very nice and my pleasure to meet with you online to conduct this course. And this course is for training in advanced capabilities in electronics design and in manufacturing. And the topic of my course is Introduction of 4G, 5G mobile phone. And my name is Wei Hao Qiao, Zhong Wei He in Chinese. And here is my contact information. And hopefully that with the study of this course, you get a better understanding of how 4G and 5G mobile phone is working. And also, of course, the 4G, 5G system by itself is a huge framework which includes a lot of things. It has the network side and also has the user side devices. And I'm going to walk with you through the process so that uh, you get a good understanding of the system. Here is a little bit about myself. I get my bachelor's degree in electrical engineering from National Taiwan University and also master's degree from National Taiwan University too. And then after a while, I went to the United States to UCLA, Los Angeles, to get my PhD degree in electrical engineering. And currently, I'm a professor in electrical engineering at National Tsinghua University. I used to have joint appointments in National Taiwan University and also National Taipei University. And then I was a assistant professor and also associate professor in academia sinica, and I've been doing wireless communications, transceiver designs, and signal processing for quite a while. Okay, so firstly, I like to bring to you the cellular network architecture. Of course, before we get to the details of each component, it is always the case where we get to understand the whole framework. And cellular network framework is actually a very huge framework that covers uh, a area, a region, or uh, a country, or even intercontinents. It covers even globally. Nowadays, the cellular network has been uh, very widespread in use, and then it covers uh, almost the all everywhere in the world, so that you can communicate effectively in uh, almost everyone in the world, as long as you have the contact information, for example, the phone number or the messenger ID and things like that, and you can communicate with them. That is all attributed to the development of cellular network. Okay, so the firstly, let's get an overview of the cellular network. Uh, the this is the progress of the network. It actually develops quite early in the century. Even in early days, let's say at the beginning of 19th century, there was there was First World War and then the Second World War. In the war, in the war, the battle zones, the battlefield, wireless communications helps to coordinate the military stuff. So it was actually a very instrumental and very important in terms of the battlefield operations. But after quite a while, after a couple decades, now it goes to 1980s. There was the 1G technology, and that 1G technology, it has a requirement of less than 1K bps, and this bps stands for bits per second, and that was in the 80s. And then the second generation, which covers 9.6 kbps, that was in the 90s. And that 9.k, if you think about this with the voice rate, the sampling rate for voice, this 9.6 kbps is just right fit into the application of voice. So that 2G substantially supports the voice communications. That was in the generation of 90s. That was the first thing, of course, first thing people like to do, which is to support voice. So it enables remote wireless communications by voice. That's a basic requirement. And then when the generation comes to 2.5, it supports 10 to 150 kbps. That was in the year around 2000. And then up to the third generation. The third generation is around 2000 to 2010. That was when people start to use the cell phone to serve the web, to serve, for example, the data communications. It was uh, of course, it's very sufficient in terms of supporting voice communications. So people have no problems with voice communication at that 3G generations. As you see, the data rate is substantially higher than the voice requirement, which is 9.6 kbps. Nowadays, uh, uh, people demands more. People demands, for example, web service, data communications, multimedia, messengers, things that requires a lot of data rates. So if you see 144 kbps, that was just right a little bit uh, good. It's just right fit to the data communication, barely meet the requirements. And then up to 2 mega bps, that will fully support the data. But up to 4G and 5G, people demands more because we not only need to demand the data service, we also demand the service to be efficient, immediate, and fast. We like the data to go fast. So it the requirement would be 100 mega bps to 10 giga bps. And that's the 4G, 5G requirements. So for example, you can expect to download a movie maybe in a few seconds, in 1 to 2 minutes. That's the requirement. Not to mention that you can watch things online, video online, real time, without much delay. That is 4 to 5G, and that if you check that uh, time period, it's going to be around 2015 up to now, 2020, and it's ongoing. It's ongoing. Okay, so the cellular network, from generation to generation, it has different requirements. So from 1G to 5G, the first generation in the early 80s, and it's analog transmission because the primary thinking about wireless communication is to help people to communicate by voice. So as you can imagine, it was using analog transmission because it was simple, it was easily implemented through simple IC. And of course, by that time, the semiconductor technology very was not very advanced. So as a result, it's unlikely that we can implement very complicated IC as we do today. So primarily, it will serve speech communication, and the terminology is AMPS, Advanced Mobile Phone Systems. And then the second generation at the 80s to 90s, it was digital transmission. And then uh, when it goes to uh, digital, we can talk about its data rate by bps. As you can see in the beginning of the first generation cell phone, it doesn't specify the data rate because it's an analog system. And an analog system, it will just transmit the information via analog format. And so to speak, that will be the best effort, uh, transmission by best effort, no guarantee of the quality. And of course, if interferences or noises come in, then the signal is going to be jeopardized, degraded. There will be no guarantee. But uh, when it comes to digital communications, we start to talk about its bit rate. So uh, primarily, uh, the the rate will be 9.6. That's just barely good enough for voice. And then the data rate is low, of course, at the beginning. People just want to make it work instead of making it good. Then that will be GSM system or IS-95 CDMA system at that time. And then uh, PCS, low cost, low power, low mobility applications, two formats in that time. And then there will be a intermediate generation 2.5. That's 2G evolved to medium rate, smaller, which is smaller than 100K. So as you see, from 9.6 up to 100K, it's been a very huge jump in terms of the data rate. So it's a uh, advanced advancement. Of course, from the perspective of nowadays, it was not that advanced, but it was considered very advanced at that time. It almost 10 times the data rate. at that time. So uh, it, for 100k bps, it supports a lot of things rather than just voice. And then up to 3G, it will be future broadband multimedia, and it's 144 kbps up to 384 kbps, and also it supports I'm sorry, it supports this property, which is high mobility, high coverage. So in the old times, uh, people have not considered mobility. So let's say if you sit in a car and you drive fast, you may lose connectivity at that time. But this third generation uh, start to consider mobility and also the coverage so that it supports mobility so that you can move the channel is going to be re-estimated, and then you still get connected. Of course the quality was not that good at that time. You still lost connections from time to time if you move too fast, or you're going through a tunnel, or if you go through the boundaries of the cell coverage, then you lose some connectivity. And for low mobility and low coverage, it will be 2 Mbps. And 4G to 5G still ongoing commercialization, R&D, and also research. A lot of uh, work is still ongoing in terms of 4G and 5G. And then, as you may know, or you may be using some of it, which is to include message, web, voice, multimedia, online streaming, or some people may be using even more advanced applications such as virtual reality, healthcare, remote healthcare, remote diagnosis, and things like that will be all can be enabled by 5G. Okay, so now let's go to the some of the issues. This is a bit more technical uh, in the cellular communications. So the issues, uh, for example, frequency allocation will be an issue. Imagine that you have a lot of users nowadays. In the old times, only few people can use it because it's very expensive and because it's only limited to some, for example, military government applications. But when it comes to commercialization, uh, we have to accommodate a lot of commercial users, end users, such as you and me, regular people, in the society. Almost everyone wants to be covered by the cellular system. So uh, frequency is very limited by nature, because frequency by itself it's it's a physical entity that is limited. So frequency allocation will be a big issue if we want to accommodate a lot of applications and people. And also it could be licensed or unlicensed. For example, ISM band is unlicensed, and there are many providers. So providers compete with each other to get more license. They may have to pay a lot of money for authorization to use the license. And there are multiple access technologies just because there are many users. So we will not be able to say, uh, if you are using the phone, I cannot use it, right? We need multiple people to be able to use it simultaneously, right? So uh, we definitely will need some kind of multiple access technology to to allow people to connect, to communicate same location, same time. So that's the multiple access technology. And also we need wide area of coverage. It used to be the case when people can only be covered within a limited area. How come? Because uh, the technology was not that advanced. So we have no choice if we want to be covered, usually in the small city areas instead of suburban areas. Usually cities will be covered first, then it spread out to wider area. And then the traffic management. By traffic, we mean data traffic. So how do we manage the data, right? If a lot of people are using it at the same time, then data could come in same location, same time, and it causes a jam, like a traffic jam in the road, right? So we need some kind of traffic management technology to manage the data traffic. And then uh, the location management, because uh, we have high mobility in cars, in trains, and even some people expect to be able to use it in an airplane, in a flight. That would be even higher mobility. And we have multiple suppliers and also handoff management, roaming. How should we uh, control the handoff? So for example, you are roaming from a city to another city. You're going to go through a process of handoff. Your data connection would need to be moved from city A to city B, right? So that's a roaming technology. And then there will be uh, the general principle which handles those things differently by different generations. So let's get an overview of multiple access technology. How to allocate users. So for example, the time and frequency will be the resources for uh, as the communication resource. The time and frequency are the fundamental resources in this communication. So we can look at the time dimension and frequency dimension. So the frequency division multiple access is to use the time. When the time is ongoing, the users are put into a different frequency band. For example, user 1 into session 1, into user 2 into session 2, user 3 into session 3, so on and so forth. So each user is put in different frequencies. That's called frequency division. Then if we look at this block here, we have time and frequency, and this is called time division. So for example, user 1 is put into this session 1, which is the at time slot 1. User 2 is put into time slot 2. User 3 is put into time slot 3, so on and so forth. So you may ask, then how would user 1 communicate? It seems to be disconnected in time, right? But the answer is it will repeat. The pattern repeats itself. So for example, user 1 will be connected here, and then after a while it will get a chance to transmit again, and then after a while, periodically, you will get a chance to transmit, so on and so forth. User 2 applies the same. It it gets a chance to communicate, and then gets a chance to communicate, and gets a chance to communicate periodically. And because the time period is short, so in a human perception, we will not be able to tell that it's communicated in discrete time. Well, technically it communicates in discrete time, but in human perception, we will perceive that communication as if it is continuous. So that's sort of technology, and that, as you can see, it's uh, the users are put into resources in different time, and that's called time time division, time division multiple access. Okay, that's the time division. And if you use code division multiple access, all people are communicated uh, in sorry, all people are communicated in the same time using the same frequency, except that they are code divided. They are code divided, so it's called code division. Then how would the code be divided? We use orthonormal codes. Those codes are independent with each other when they do inner product. So to put it briefly, each person will be assigned an individual code, and those different codes are orthogonal with respect to each other. So when the receiver receives that information, it can decode the information of an individual user by doing inner product for the code. That's called code division. And then a cellular network works like this. You have a cell, you have a cell, and that cell has a base station, which is called base transceiver station. Sometimes we abbreviate it as base station. And that base station communicate with mobile user. Here is the mobile user. Communicate with the mobile user wirelessly. And then of course you can see multiple users are communicating with the base station simultaneously. And that's what we mean by how this multiple access techniques is working. It communicates using the multiple access technologies. Then the base station uh, will communicate with the switching center. That switching center is kind of like an operation central office at the telecommunication company, and it's usually uh, with high standards. For example, the electricity, the UPS, things like that will be constructed with the switching center to ensure that switching center is highly reliable. So the users communicate with the base station, then it goes through the switching center. Then the switching center could communicate its information to another base station, and then another base station will communicate with the user, so that uh, multiple users in cell 2 will be able to communicate with cell 1 through the relay for the switching center. Okay, so here's the wireless part, and then there will be wired communication, which is the P PSTN, PSTN, and that PSTN is the wired system. It's sort of more conventional. Uh, in some countries, uh, they don't even have to go through the PSTN stage. They will construct the wireless network from the beginning, and then they use the cellular network from zero. But in some countries, they have PSTN as a legacy, as a legacy. So uh, people would need to with the wireless, communicate wireless user with the users in PSTN. Then it has to again go through this switching center so that it communicate with the PSTN user. And then of course, uh, hinged on the switching center is the home location register and visitor location register, so that those are databases to register the information of the users, so that when the users has some location information, configuration information, they will all be registered in that databases. Okay, so uh, for the location service, uh, it's a cell ID based. This applies not only not only to 2G, 3G, even 4G, 5G. It's a general architecture to do the location service. So the cell ID will be assigned, and then but of course, it's hidden in your background of a cell phone, so you wouldn't get to know it. You will not get to know it. But if you are an engineer or you are engineering on the system, then you will get to know the ID. So there is an ID here, and the ID is stored in a database. And then as you move from one cell to another, you assign a different cell ID, and then location database is updated. The most commonly used in cellular network. So for example, the home location, the visitor location, and neighborhood pooling, the connected mobile units only move to adjacent cells. So for example, you lose your connection with the base station, then the system will start to pool your neighborhood because the connected mobile users move to adjacent cells. Then geographically, that's reasonable, right? You only move to your neighbors. It's not like you jump in a second from here up all the way to a location further away. Usually, you only move to your neighborhood. Then angle of arrival, the angle at which radio wave from your device reach an antenna is used to calculate the location of a device. So for example, if you your uh, angle of arrival from this direction, then the base station and also the switching center will get to know that you're at this location rather than the other location, right? Because it knows it gets to know your direction, then it roughly will get to know your location. So that's the angle of arrival. Time taken. The time taken between device and antenna is used to calculate location of the device. And of course, you know, the uh, el electromagnetic wave is assumed to travel at the speed of light. So if you know the time, then most likely you do a calculation, you get to know the time packet, and then you get to know the distance, and you get to know the location. And then there is also a network assisted global position system. A GPS is installed inside a phone, and that the location of the user is tracked. So for example, you put a GPS here, and periodically from time to time it will convey its location information back to the base station, and it goes to the registration here, goes to the database registration. Then you get to know, uh, people get to know your location. Okay, all right. So hand off, hand off. Uh, At any time, mobile station is in one cell and under the control of a BS. It has to be this way. It's not like a mobile device is moving along. If it's moving along, then no one is going to get connected with him, right? So, mobile station is under the control of a base station. When a mobile when a mobile device leaves the cell, the base station notice weak signal. So for example, this person, if it's moving here, then its signal is getting weaker and weaker, and then it's getting a weak signal. But the surrounding base station will get a strong signal. For example, this guy is moving at the boundary, then it's going to get lost with the original base station pretty soon, and then it will get stronger and stronger signal with the neighbor base station. So the base station will ask if surrounding base station are getting a stronger signal. Then the base station transfers its ownership to the one with stronger signal. Then the switching center assigns new channel to the mobile device and notifies the mobile device of the new boss. So for example, this person goes to here, then this will be his new boss, and then he will assign a new channel to this person, and then also notifies uh, this space station is the new boss, so he will communicate with this new one. Then the concept of frequency reuse. The frequency reuse is based on assigning to each cell a group of radio channels used within a small geographic area. So cells are assigned a group of channels that is completely different from neighboring cells. The uh, so for example, in here, when this space station is using some channels, the channels will not be able to be used by this cell, right? The reason is that if the neighbors are using the same set of frequencies, they interfere with each other. So uh, so that's why cells are assigned a group of channels that is completely different from neighbors. Because if the neighbors are using the same frequency, they interfere with each other. And the coverage area is called the footprint and is limited by a boundary, so that the same group of channels can be used in cells that are far apart. Let's say if a cell is using some frequencies here, a cell far apart can reuse it, but the neighbors cannot reuse it because when the neighbors are reusing it, it will cause interference. So we should have this brings up the concept of coverage. Of course, then it depends on the power. If this looks like a reasonable coverage, while in reality, the coverage may not be so ideal. The coverage may go like you know very strange area because we cannot control the electronic magnetic wave. You know, when you transmit it, it's out of control. We can only control the power, so that is somewhat limited within that area. So the concept of the boundary, that is usually, ideally, we put it into a hexagon, but in reality, it could be a very strange area. So cells with the same number have the same set of frequency. This is the concept of frequency reuse. So for example, uh, this cell number 1 uh, using is using the same set of frequencies. The reason is that those things are considered far enough, so we reuse it and expect little or no interference. So there are two things you can see here. First thing is we need to reuse it. We don't have a choice because if you don't reuse it, then we are running out of frequencies, right? We need to accommodate a lot of users, but our frequencies are limited, so we have to reuse it. And the second thing is if you reuse it closely, they interfere. So there is a trade-off between efficiency and accommodation. We need to reuse it while we need to reuse it remotely. So you see cell one, and then when it's far away, we reuse it again. But uh, it's not like we can reuse it arbitrarily, because if you do it that way, you have interference. And again, we can see cell 3. Cell 3 reuse it further away. It's not like you use it here and then use it here. That's not the case. And you see cell 5, reuse it far away, reuse it far away. And then the same applies to all the cells. So to put it simply, we are reusing it in a simple way, but yet we need to consider the efficiency. Okay, so here is another example: frequency reuse using 7 frequencies allocation. Each cell is generally 4 to 8 miles in diameter with a lower limit around 2 miles. This is in the older generations, for example, 2G, 3G. Nowadays, uh, for example, 4G and 5G, it tends to use a smaller size. For example, 300 meters, 500 meters. We use smaller cell size so that it can be reused more frequently. So here is an example for frequency reuse using 7 frequency. So we have F1, F2, all the way up to F7. And as you see here, as you see here, uh, F7 is reused here, F7 is reused, then uh, remotely with a certain structure, and F1 is reused with a certain structure, right? And then if we look at it one more time, F6 is reused remotely again. Okay, so this is the reuse, a pattern of reuse. And then we will see uh, different cluster size. So for example, here is a cluster size of 4. So it has 4 sets of frequencies. And you see 1, 2, 3, 4, 1, 2, 3, 4 repeating. 1, 2, 3, 4 repeats itself. And then 1, 2, 7, 1, 2, 3, 4, 5, 6, 7 repeats itself, and then repeats itself, and repeats itself. Right? And if we have a larger cluster size, for example, 19, it's hard to, it's hard to draw the details out, but we have 19 here. So 19 repeats itself again for a cluster of 19. So as you can see, the design of the reuse pattern is by itself a topic of research. If you use it uh, in a smart way, you get a better reuse efficiency with little interference. If you reuse it uh, in a not so good way, then you get uh, interference. You get interference. For example, if you happen to put 1 at the neighborhood, then you get a lot of interference. And as you can imagine, 19 is a bit more difficult to allocate, so that uh, it gets complicated. But yet, if you use the cluster size to be larger, then uh, you could improve its efficiency because uh, you can separate it further away, then you get better reuse efficiency with less interference. Okay, I think that will be good for this first hour, and we take a break for a couple minutes, then we will come back. Yeah, let's come back later.